Hello students, my name is Shashank Shekhar and today is the fourth lecture of the chapter Hello Alcohol, Phenols and Ethers. So if you look at the syllabus here, so we have covered this part, that is our nomenclature, methods of preparation, physical and physical properties. Now we are left with this chemical properties. Today we will be seeing mainly this chemical properties, and I think this one is the most important one, that is the identification of primary, secondary and tertiary alcohol. And then we will see the mechanism of hydration in reference to your methanol and ethanol. So you will not see the uses today. Okay, about methanol and ethanol. So basically, we will be seeing the chemical properties, and especially our focus will be on dehydration reaction and your identification of primary, secondary, and tertiary alcohols. Right. So let us start our today's class. So for that, let us look at the topics. So basically, we will see what is the structural aspect of the alcohol that makes it reactive. Then we will see two types of reaction. First reaction which involves the cleavage of OH bond, and second reaction which involves the cleavage of CO bond. Okay. Now under this we will see various reaction. Under OH bond we will see various reaction, and under CO bond cleavage also we will see various reactions. After that we will see the mechanism of hydration and dehydration. So we will look at the mechanism of this particular reaction because it's important. So let us start our today's class. First of all, about the reactivity of alcohol. So if you look at alcohol, it has two bonds which are present for oxygen. One is between O and H, and the second one is between R and O. So two types of cleavage can be done, OH and RO. And based on this, we have our two types of reaction. So if the breaking of bond takes place between O and H, then the alcohol acts as nucleophile. And if your say this breaking of bond takes place on the basis of CO bond cleavage, so this bond is broken, then in this case this alcohol act as an electrophile. So due to this reason, this can act both as a nucleophile and electrophile. So they are versatile compound. Now the bond between OH is broken when alcohol act as a nucleophile. The same thing is written, and when it acts as an electrophile, the bond between C and O is broken. Clear? For this should be not here. Yes. So you can see a reaction here. Now what is nucleophile? First of all, you should have the clear idea of what is nucleophile. So nucleophile is something which is nucleus loving, and you know it very well that which one will be nucleus loving. That will be that which has negative charge, because loving means it is attracted to that. So basically nucleus is positively charged. So if something is attracted to positive charge, so it must be negative, because opposite charge attract each other. Now, if you think of the entity which is carrying a negative charge, then you would think of electron. Okay. So an oxygen has electron in this alcohol structure. Then these are lone pairs. Okay. Two lone pairs are there. So this lone pair can attack on a nucleophilic center. So this is the nucleophilic center that we are considering, since this carbon has three bonds. So three electrons are here and one of the electron is missing. So it has a positive charge. So there is, this is the nucleophile in this case, and this is the electrophile. So this is the nucleophile and this is the electrophile. Right. Now the attack takes place. So if you see here, sorry. Yeah. So if you see here, you can see that okay, there is a arrow. Now I mentioned it earlier, I'm mentioning it again. So the tail of the arrow is basically the source of electron, and the head of the arrow is the place where the electrons will attack. So here the oxygen is the source which has a lone pair, and this carbon has an empty p orbital due to the removal of one electron. Okay, so there is an empty p orbital. Now this empty p orbital of carbon, so if you look at the structure of carbocation, so it looks like this. So I am mentioning because it's very important to see the structural aspect that would make it more easier to understand why does this attack take. So a p orbital, a vacant p orbital is present. Suppose this is x-axis. Okay, right. So there are three bonds. So it has a kind of planar structure. And if you talk about geometry, so it has trigonal pyramidal. So basically this say our orbital is vacant. Since it is vacant, it can accept electron. So this oxygen has a lone pair. It donates its electron to your empty orbital of carbon. Now this would make a bond between O and C. But since one electron has been donated by the oxygen to this carbon, and therefore it now carries a positive charge along with it. It carries a positive charge along with it. Therefore, further what will happen? This H that was initially there on oxygen will be deprotonated or removed. So the species is now deprotonated and we get this kind of structure. So it can be ether. How? If R is suppose CH3, then the structure is called ether. The ether is basically a compound that contains oxygen between two carbons or oxygen bonded between two carbons. Okay, and this H has been released. So this is the overall reaction where alcohol acted as a nucleophile. Now the second case which I have told is that the bond between C and O is broken. So how it is broken? So for that, first protonation of alcohol takes. So this is our alcohol. Okay, now I have told you earlier that this oxygen can donate its electron. So it donates its electron to H plus and we get this type of reaction. So basically if you look at it, it looks like an acid base reaction. This is the acid, this is the base. So from here you can say that alcohols act as a base. Clear? Because they can donate its lone pair. So it is a kind of Bronsted base. So we'll see it in the next slides or the coming slides where we see the acidity of alcohol. For now, just consider this is an acid-base reaction and alcohol is acting as a base and H plus is our acid. So that would result in protonation of O and O will now carry a positive charge. So therefore now if you have a say nucleophile, in this case we have used Br, so it has a negative charge. Now it can attack here. And now OH2 plus can be released in the form of OH2. It is water molecule. And this is a very good living group. Therefore, we will get our halogen containing compound. Okay, or alkyl halide if this R is not benzene. Okay, so this is the reaction. Now, if you see here in this step, we can see that this bond isn't broken between C and O. Clear? And here you can see that this bond has been broken in this step. Okay, so here is an OH bond. It is broken and we got this. So these are the two types of reaction possible due to two type of bond cleavage. First is between your carbon and oxygen, and second is between your oxygen and hydrogen. So for carbon and oxygen, we will get this kind of electrophile. We will get this alcohol will act as electrophile, and for OH cleavage, alcohol will act as a nucleophile. Now let us study each of them one by one. So first is your reaction involving cleavage of OH bond. So for that, let us take the example of reaction with metal. What we have done, we have reacted our alcohol with metal. So here is our reaction. This is our alcohol. We have taken a general form of this, that is ROH. R can be anything. And anything means it should not be SR3 or something like that. It should be something that has C bonded on the first place, and then the group further can be anything. Okay, clear? Now it is reacted with a metal, say sodium. So what will happen here? Now this sodium will be now attached to this O, or you can say it will donate its electron and kind of form a alkoxide. It's called alkoxide and H2 gas will be released. So basically here the alcohol is acting as a base and Na is acting as an acid, and the release of H2 gas and the formation of salt. This is salt. Clear? So we can react it with sodium also, or we can react it with aluminium also. Now since aluminium has a valency of 3, so 3 of these alkyl groups, okay, 3 of this alkyl group. So total, according to this stoichiometry, you can see that 6 moles of your this tertiary butyl alcohol reacts with 2 moles of aluminum to give 2 moles of aluminum tert butoxide. So if you see for 1 mole of this, then 1 mole of this compound would need 3 moles of this, say, group, or 3 moles of this tert butyl. You can just imagine like this, just divide by 2. So that would result in, here 3 will be occurred, here we will get 1, here we will also get 1, and here we will get 3 by 2. So basically 3 moles of tert butyl alcohol react with 1 mole of aluminum to give 1 mole of aluminum tert butoxide. Again, it is why tert butoxide, because here is a tertiary section. Your tertiary section which is attached to your OH. Here also the tertiary section is attached to O, and you can see that in both this reaction the cleavage of OH bond has been taken place, has been done. So here OH bond has been cleavaged and Na has been introduced. Here also OH bond has been cleavaged and Al has been introduced. Now this above reaction shows, so since it is an acid base reaction and this alcohol acted as a base, so you can say that alcohols and phenols, both of this. Okay, so we will talk about phenol in the later class. Also, we will discuss their or you can say compare their acidity. So for now, just take it for granted that okay, this alcohol and phenol both can react with your metal and give your salt and hydrogen gas. Or you can also think it in the form of Bronsted acid and Bronsted Lowry concept. You can think it in that way also. So this is the base, then this is the conjugate acid, and this is the acid, then this is the conjugate base. So in this fashion, they are related to each other. Clear? So here our base is your alcohol and your so yes, the base is your metal and your alcohol is your acid. We got the conjugate acid where now we have this thing, and for conjugate base we have alkoxide or butoxide. So this is the proof that this alcohol is acidic in nature. And also in each of these reactions we have seen the cleavage of O and H bond. Now let us compare acidity of alcohols. So the acidic character of alcohol is mainly due to the polar nature of OH bond. So since this O and H bond is polar, so it can be uh, dissolved in some polar solvent to release H plus. And plus we have an electron releasing group. So this increases the electron density on oxygen, tending to decrease the polarity of OH bond. Now how is this polarity order? So it has a delta negative charge and it has delta positive charge. Now if we introduce CH3 in front of this, then they will donate electron. If they will donate electron to this oxygen, clear, if they will donate electron, increase electron on this oxygen, so that would destroy the polarity of OH bond, and this decrease the acidic strength. Clear? Because since they will donate electron on oxygen, it will create a delta negative charge, greater delta negative charge, which will be later passed on to this H, and this polarity will be destroyed. The acidic strength of, so if we take this concept, then the acidic strength of alcohol would look like this, that the primary, if only one alkyl chain is attached, it will be the most acidic one. Two alkyl chain, it will be in the intermediate, and third will be very less acidic as compared to these two. As you can see, we can have a double arrow sign, means much more less acidic than the secondary alcohol. So this tertiary alcohol is much more less acidic than the secondary alcohol. Clear? Now alcohols are however weak acid than water. How we can say prove it? Just react your alcohol with water. So it can be illustrated by the reaction of water with an alkoxide. So you can see that here your alkoxide reacts with water to form the conjugate acid and conjugate base. Now how can you derive that okay, this is a weak acid or weak base? So basically this reaction is more favorable in the forward direction. Okay, this reaction is more favorable in the forward direction. Now what does this mean? That this ROH is more interested in is more interested in being in this form rather than this form. So if it would have preferred to go to this form, then we would say that okay, this would act as a better acid. Sorry, yes, better base. But it is not so. Instead, instead we have seen that it is more favorable in this form. Clear? So it is acting as a acid, and the water is acting as a base. Sorry, OH1 is acting as a base. So this can be seen from this. Now this reaction shows that water is a better proton donor than alcohol, and alkoxide is a better proton acceptor than hydrogen ion, which suggests that alkoxide are a stronger base. Therefore, now alcohols are also act as a Bronsted base as well. So here in this reaction, in the previous reaction, they have acted as a Bronsted base, but here the acidity of your water is greater than alcohol, and it is obvious because this oxygen has H on both sides, hydrogen. So they are not electron donor. Due to this, the polarity of the OH bond is not affected that much. But in this case, we have R that can be carbon, and it donates its electron to this OH bond, and its polarity is disturbed. Therefore, it becomes less acidic as compared to the water. Clear? So this is the reaction. Now, how we can compare the uh, say acidity of different alcohols? So basically we have a common trait, that is primary, secondary and tertiary. Otherwise, if there is not such comparison, then you will look for things like alpha hydrogens, or you can say resonance and all those aspects. Clear? So this was the reaction involving cleavage of OH bond. Now we'll see the esterification reaction. So here also a kind of OH bond is broken, but this reaction is very important. So basically, it is for both for alcohol and phenol. So I'm considering both of them. So for those who are unaware about the structure of phenol, so it looks like this. Okay. Now they react with carboxylic acid. Sorry, they react with alcohol. This phenols react with each other. You can say carboxylic acid. This phenols react with carboxylic acid to give your acid chlorides and acid anhydride. So depending upon our substrate, they will get our reactant. Okay. So first reaction, you can see that okay, we have a ROH and we reacted with R-COOH. So what will happen? So we will get the esterified product, that is this, and its structure will be R-COOR. So structure will look like this. Okay, and since we do not have this second part, if we reacted it with anhydride, then the product would have been different. This H2O will be different. But since there is OH remain, so this OH take also one H plus, and we get as H2O. Second, we have again we have taken your say alcohol or phenol. We reacted with acid anhydride. So in this case, we get one ester and plus one carboxylic acid. So we'll look at the mechanism to get a clear picture of this. Next, we have AROH, and if we react it with acid chloride, but in the presence of pyridine, we have taken a base here. Then we will get your ester plus HCl. Now let us look at the mechanism why it happens. So the first reaction was your reaction of alcohol. Okay, we have an alcohol, and what we have done, we have reacted it with acid, and in the presence of your H plus. So we have taken a mineral acid along with it, as H plus. Now what, where will this H plus go? So it should be very clear. So this is more suppose this is more basic than this one, because this is your carboxylic acid and it is more acidic. So it will accept your electron. So what we will get? We will get this kind of structure. Yeah. Or what can happen? So this is the first case. So we are taking both scenarios. Now can you imagine that this lone pair will attack here? No, it will not happen because this lone pair is being reasonated throughout the carboxylic acid. But one thing should be always in your mind during doing the mechanism of reaction, that both possibilities are possible. This can go on this also and on this also. So both of this will be formed. Although this equilibrium will be much shifted towards this one, but this is also a possible your product. It will be present in less amount, but it is possible. Therefore, we are left with an alcohol. So we will take this one because that one is not favorable for nucleophilic attack. Plus, the carboxylic acid is not a good nucleophile, but your alcohol is a good nucleophile. Okay, so therefore, as a time we get this thing, the alcohol quickly attack the lone pair of oxygen, quickly attack your carbonyl center. This gate here, it resonates back and your OH2 plus is released, and we get this kind of structure. So this is R. Okay, and we have an H plus again. But since it is an acid catalyzed reaction, this will be deprotonated and we will get back your ester. This is the mechanism or the esterification. Okay. Now the second one was anhydride. So anhydride looks like this. This is the structure of anhydride. Suppose we take as R double dash and ROH. Again, we have two possibilities, either protonation of this or protonation of this. But since this is not a good nucleophile, will not attack because this is resonated through now both carbonyl. So now it has become almost least nucleophilic in nature. Therefore, the H will go here. Now, as this H will be attached here, this will increase the nucleophilicity of this center. Okay, and now the lone pair of this O will attack on this nucleophilic center. So this would result, this bond pair will go here, and this will result in this thing. Clear? Okay, and we have a ROH. This thing has happened. Now, what will happen in the next step? In the next step, your H will be here. So it will resonate back and kick off this thing. So it will be kind of a interproton transfer, IPT, intraproton transfer. Therefore, the H will go here and we will get your, this is the R dash, R double dash, let it be R. This is R dash, we will get OR here. Again, this H will be more deprotonated, and plus we will get a carboxylic acid. So this is the second one, and the third one was chloride. So we use basically a pyridine there. So that should be remembered. We have used a base. So why we have used a base? Let us see. Okay, let us see. So basically, what would have happened if we have used an acid? So basically, what happens here, that if we have used an acid, still it would not become a good nucleophilic center. So instead, we have used base. So what will the base do? Now this base will react with this alcohol. Your pyridine is a base. It looks like this. Okay, it is a base and it has a lone pair. So it takes the H of this. First, this and this will react. This will result in RO minus plus your protonated pyridine. Now this RO minus is a very better nucleophile than your simple RO because it has now a net negative charge. Now this RO minus will attack on this center. This bond pair will go up, it will revert back, and this Cl will be kicked out. So you will get, suppose this is R dash. Okay, this is R dash, R dash. Therefore, we will get this thing. Okay, so this is our product. Plus, what will be formed? Your HCl will form. We have our Cl. This Cl minus will take this H and we will get the HCl and I'll get our pyridine back. So this is the way all this reactions takes place. Okay, so I have done this mechanism to make a more clear picture, because instead of remembering that what is to be used, you must be aware about the, say, your reagent functionalization, that is the mechanism, and that would be more beneficial for you also if a question comes that is out of your way, so that you would be able to tackle it if you know the mechanism. Now, the reaction with, again the same statement is written, the reaction with carboxylic acid and acid anhydride is carried out in the presence of a small amount of concentrated sulfuric acid. So both of this reaction involve the use of H plus, and the H plus is now facilitated here by H2SO4. Now the reaction is reversible, and therefore water is removed as soon as it is formed. So this H2O is removed. Why? Because you can see a reversible sign here, because it can again attack this say ester and do the acidic hydrolysis, and hydrolysis of this ester will give back you this thing. So as soon as this water is formed, it is removed back. And the reaction, and if you talk about the third reaction, sorry, the reaction with acid chloride is done in the presence of base so as to neutralize the HCl which is formed in the reaction. It shifts the equilibrium to the right hand side. So what happens? So instead of removing this HCl, we have used a base. Now this base will neutralize. So since we have used base, this will neutralize this HCl that is formed during the reaction, and hence the equilibrium will shift to the right, because we have moved to the removed the product, and you know according to Le principle that now the reaction will move in the forward direction to facilitate, or you can say uh, compensate the removal of the product. Next, the introduction of acetyl group in alcohol or phenol is known as acetylation. Okay, this is called acetylation. So we'll see this reaction in the next part. Sorry, this is not of your concern right now. When we will see the reactivity of your phenol, then we'll see with both of the statements. Now let us move to the second type of reaction, which involves the cleavage of CO bond. So it phenol shows this reaction only with zinc. So if we react it with halogen halide, so first is the reaction with halogen halide. Second, phenol, we have written about phenol also, but we will not talk about it more. So it is basically written that this cleavage of CO bond for phenol takes place only if we use zinc. But for alcohol, we have many methods, such as reaction with hydrogen halide or reaction with phosphorus trihalide. You must have seen this reaction during preparation of your, say, halogen containing compound. Then we have dehydration, and then we have oxidation. So we'll see oxidation in the next class. So today we basically dealing this dehydration mechanism mainly. Okay. So first of all, the Lucas test. So I have mentioned in the starting also that this is the important one. Why? Because questions are being asked often that, okay, identify the compound or identify that whether it is primary, secondary, tertiary. So that can be done if you know this test. And I have told you earlier that this reaction is used for the preparation of your halogen containing compound, and this is the best method because both the product are gaseous in nature, so there is less problem regarding your removal of your side product. Okay, so what happens in this reaction? The hydroxy group of an alcohol is replaced by a halogen group. So this is the hydroxy group, it is replaced by a halogen group on treatment with thionyl chloride. So this is called thionyl chloride means thio is used for your, say, sulfur oxygen. So if we treat it with thionyl chloride, then we get this thing. And for your information, I would say that this follows SNI mechanism. So since I have shown the mechanism, you can try this by yourself. I am just giving you a hint that this O will attack on S. Since it is an MTP orbital, so it will attack on S. This is the first step. Now carry out the further by yourself. Now thionyl chloride is preferred because its reaction involves alkyl halide is formed along with gases SO2 and HCl, which escapes the reaction mixture, and you do not have to worry about the separation technique. Now the two gases product are acceptable, hence the reaction gives pure alkyl halide. Same thing written. But why do we use it as test for primary, secondary, and tertiary? So the reason behind it lies in the time taken by the reaction. So the reaction of primary and secondary alcohol give HCl requires the presence of ZnCl2. So if you react it with ZnCl2 simply in the presence of HCl, so primary and secondary would require ZnCl2, this catalyst. But if you react with tertiary alcohol, the reaction is conducted by simply shaking the alcohol with concentrated HCl. So basically the timing between all this reaction varies for primary, secondary and tertiary. So for primary, basically this reaction almost is very slow. For secondary, it takes place in 5 minutes, but you have to use the catalyst ZnCl2. But for tertiary alcohol, you do not have to use the catalyst also. If you just treat this tertiary alcohol with your conc HCl, you will get your alkyl halide. So this is the reaction. Although you can use ZnCl2, but to identify the primary, secondary, and tertiary, we have to introduce this ZnCl2 and remove this ZnCl2 and see both the cases. Now, if you see the reaction with HBr, so we can just react constant boil it with HBr to prepare alkyl bromide. You do not have to introduce such a catalyst, and Ri can be formed just by heating with sodium or potassium iodide. So for reaction with Ri, so if you want to if you want to get Ri by reaction of ROH, you have to treat it with sodium or potassium iodide in 95% of the phosphoric acid. So as I have told, the order of reactivity would look like this. That is 3 degree first, then 2 degree, and then 1 degree. Okay, and the reason is obvious because it kind of has a SNI reaction. So if you look at the mechanism, you will get an idea why is this so. So if I just give you a gentle initiation, so it will look like this. That since the first step is the attack of oxygen on your SOCl2, and for that the oxygen bond should be polar. But since we have the oxygen should contain more electrons. Now since if it is tertiary alcohol, it will contain 3 R groups. Now all of these 3 R groups will donate its electron to oxygen. Therefore, it will be electron rich and it will be easier for oxygen to attack on SOCl2 as compared to 2 degree than 1 degree. So this is the reason. Okay. Now next is the reaction with phosphorus trilite. So this also follows your SNI mechanism. So it can be done both with your pentahalide and trihalide. But for pentahalide, you can take chlorine only. But for trihalide, you can take both chlorine and bromine. So basically, if you treat your phosphorus tribromide and triiodide, then you can treat this with your alcohol to get your halogen containing compound. And if you are treating with pentahalide, then you can use chlorine only. Here also, the side products are POCl3. So you should be attentive about this. Side products also, these are also important. Sometimes you can get the side products, or you can be asked that complete the reaction. Okay. Plus, we'll get HCl in this. Now, the above methods are not applicable for the preparation of alkyl halide because the carbon-oxygen bond in phenol has a partial double bond. So, if you talk about phenols, this mechanism cannot be used because you know very well that it involves the cleavage of CO bond, and we know it very well that for cleavage of CO bond, you have to break a kind of double bond, and many more technicalities are there that it cannot undergo nucleophilic substitution due to electron cloud on both sides, and we have a hybridization also, sp2 hybridization, partial sp2 hybridization. So due to this reason, it will not undergo this reaction. Now we have some other reactions also. If you treat your alcohol with NaBr and H2SO4, you will get RBr. Okay, and if you treat it with red PXP so it will form PX3 only. So basically, we have taken the reagents rather than PX3 directly. So question can be asked in this way also. The end result is same. We can use, but we can use bromine and iodine both. Okay, but we cannot use your chlorine and fluorine for this method for using red phosphorus with X. Now let us move to dehydration. So if you look at the word dehydration, it basically means we are removing we are dehydrating something, or say we are removing water from here. So this dehydration of your alcohol, it takes place, or you can say removal of water takes place in the presence of acid, and it results in the formation of alkene. So for this, we can use the catalyst also, zinc chloride or alumina. So what do we do in this reaction? Basically, we take ethanol and treat it with H2SO4 at high temperature to remove the water or to remove H2O, so that we can get an alkene. Okay. Now if you see the relative reactions, or you can say relative reactivity, then you will find that okay, this reaction goes faster for tertiary then secondary and then primary. So if you just have a thoughtful idea about it, then you can just think in one way that okay, this must have involved your SN2 reaction. Okay, sorry, SN1 reaction, because it is giving the reaction is already nucleophilic. First of all, okay, reaction is nucleophilic. There is also elimination, but for starting one is nucleophilic. Therefore, you can think that it goes through your SN1 mechanism because tertiary is giving the faster reaction. Therefore, there must be the formation of carbocation. Okay, so comparing the relative rates of primary, secondary, and tertiary is helpful because it helps in determining that what is the mechanism of the reaction, and knowing the mechanism of the reaction is very important for a chemistry student. So this is the mechanism that we have. So what happens is this mechanism. First of all, we have our H plus, since it is a acid catalyzed reaction. So first this H plus will go to O. Okay, and it will form a protonated alcohol. In the second step, there will not attack of the nucleophile. Instead, the OH2 will leave, and this is the slowest step. This is the rate determining step. So whether it is forming or not will be the deciding factor of the reaction. Okay, therefore tertiary alcohol gives faster. So here you can see that we have a formation of carbocation. Now, since and it is the rate determining step, and this is formed in the rate determining step, therefore the order would be this simply. Or I would say that if you should be more, if you want to be more careful, then only look for the stability of carbocation. Look for now resonance also. Look for hyperconjugation also. Do not only search that okay, this is 3 degree. It will give the faster your dehydration reaction. So you should be careful about it. In the last step, your deprotonation will take place, and it will release H plus because it is acid catalyzed reaction and catalyst concentration should not change. So H plus is released in this step, and we get alkene. What do we get? We get alkene. Now, if you are asked that okay, tell me about what will the configuration of your alkene, because since it is an symmetrical alkene, you do not have to worry about your configuration, that is whether it is E or Z. But what happens in case we have your say unsymmetrical alkene? For example, suppose our alcohol is like okay. Now you are asked that what will be formed. So for this, first of all, go through the mechanism. You will get this thing. Okay, you will get this thing. Now, what we have to do? We have to remove this thing, and we have to deprotonate this H, and we have to get the alkene. Now, to avoid the repulsion, it will take such configuration which has minimum electronic repulsion. Therefore, it will go to trans, and you know that trans is the least sterically hindered product, or you can say stable one. Therefore, we will get suppose okay this CH3. Now, this will result in kind of product that is E. Now, one more case can be there that we have an unsymmetrical alkene. Okay, sorry, unsymmetrical alcohol, and both sides we have different substituents. Now you will be asked that on which side the double bond can be formed. So we have two possibilities. Okay, simply there are two possibilities. You can look at it very clearly. That either this can be a double bond and this can be a double bond. Now for that, simply you have to look for the stability, or you can stability first of carbocation, and then for the acidic nature of H atom. Okay, acidic nature of H atom. Sorry, yeah. So if you look here, so this one is less acidic in nature. Okay, this one is less acidic in nature because this is showing your inductive effect. Okay, plus It has a hyperconjugation chance. It has a chance of hyperconjugation. Therefore, it will be less acidic, and this one will be more acidic, and hence this will be formed. Okay, so this is the first scenario we can take. Now, second, this is the kinetically stable product. If you look for the thermodynamic and which is the product, the more substituted will be formed. So basically, this will be formed because it is the more substituted alkene. Clear? So this is the product. So you should look for both of this. So if I want to put all things in nutshell, the mechanism of dehydration is clear. So the product that will be formed will have E configuration and that will be more substituted also. So two criteria should be fulfilled for unsymmetrical alkene. So this is an additive point for your dehydration because just predicting the reactivity series of this alcohol, different alcohol is not enough. You have to worry about the product also. You have to worry about the product configuration as well as the product regio. Regio means since two products are possible, which of these will be formed in excess? The more so, more substituted one and the trans one will be formed in excess amount. Clear? So what we have seen in this lecture overall, so basically we have seen the reaction of alcohols and in which we have two type of reactions. First, which involve the cleavage of OH bond. Basically, there the your alcohol acted as a nucleophile, and the second one is the cleavage of a CO bond, where your alcohol acted as a electrophile. And if I want to pinpoint the important thing, then I would suggest that sorry, I would suggest that this is important: esterification and your dehydration. These 2 points, these two reactions are important in this lecture. Now we are left with oxidation of alcohol. We will see that in the next class. I have just put the slides in the next class because that is complicated as compared to this, because oxidation can have multiple reagent, because I mean that oxidation can be done with the help of multiple reagent, and you should be careful about the oxidative nature of each and every reagent. So we'll see many reagents related to that. Also we'll see some reducing agents added with it. Okay, so I would teach both of that, the reducing agent and oxidizing agent, and we'll see the relative power of both of those. Okay, thank you for your time. So this was for today's lecture. Thank you.